Everybody. Good morning, good evening, good afternoon, depending on where you're joining us in the world today. Welcome to the MECI Alliance seminar series. I'm Brian Anthony. I'm your host again today. It's my great pleasure to introduce an alum of the department, Dr. Christopher Couch, who's had a very illustrious and sort of interesting career in manufacturing, in both big companies and now in new companies. So he's the CTO of Cooper Standard and also the founder and CEO of Liveline Technologies, a new company looking at, excuse me, machine learning in automation. So today he's going to share with us a little bit about himself and a little bit about lessons from the front lines, machine learning at scale for real-time process control. Chris, losing my voice, but hopefully you're not. I'll turn it over to you. Thank you for joining us.
All right, Brian, thanks a lot. Hey everyone, good to at least see the names here on the Zoom list. It's always nice to be back in Course 2 land. It almost feels like home, but there's always that feeling when I connect with MIT that there's some kind of problem set due today that I haven't done yet, and you know, the PTSD never really goes away. But it's good to be talking to you all today. So thanks for the intro, Brian. You know, I think that nobody's more surprised than me that I'm running a machine learning based company right now. I was a hardcore course 2. I was a manufacturing gearhead. I spent a lot of my career building plants and operating plants. I guess the good news is that the background that you're getting in your program teaches you math and some other skills about acquiring new skills. And I think everyone on the Liveline team is living proof that you can take a bunch of controls gearheads and turn them into ML people, which is what we've been doing. And really the entire team on Liveline, you know, only recently with a few exceptions, are not classical data scientists. We're a bunch of engineers that have had to really invent the tech that we needed to solve the problem the way we want to solve it. And so a lot of what I'm going to talk about today is just is coming out of that experience. Again, we're not all you know, Course 6 specialists and AI. You know, we've certainly, I think, all come a long way. But we're practical, right? We're engineers. We're solving a problem. We're trying to find the best tools to do it. And I'm happy to share with you what we've been doing so far and where we're going, what some of the open issues still are for us. If you see stuff that sounds interesting, feel free to drop me a note. I've got contact info at the end of the deck today. You can always find me on the alumni portal as well. We're growing, we're scaling, and a lot of fun stuff going on that we're pretty excited about. So with that, let me start to share some slides. I'll see if I can get this in the full screen view. We good? All right, I'll take that.
Yes, it's coming through well. Yep. Very
all
good.
Right. So let me take just a moment. I'll introduce Liveline. As Brian mentioned, I have a few jobs here. One is CTO of a public company, Cooper Standard Automotive. That's a global tier 1 automotive supplier. And Liveline really came out of a few years of R&D that we had done sort of as a skunk works there. Based on the successes that we had and the potential we think we have, we decided to go ahead and set up a startup to do that, and that's Liveline. We set up the company in February of 2020, perfect timing for COVID, so we could just shut down a few weeks later in March and ice all of our plans for the first half of the year, which is what we had to do. But you know, come mid-year, we were able to get back into actual production facilities and get the wheels rolling again in terms of our pilot activity, prove what we needed to prove. And for 2021, we're in the middle of a global scale up. We've got 25 facilities that we're into in the next 9 months, and more to come in the year after that. And that's just within Cooper Standard. So busy time, a lot of fun though, and even from a technology viewpoint as well as a business viewpoint, we're having a pretty good time with it. So one of the things we often get asked is, what is it that you built? The basic answer is it's software. That's not very satisfying. So let me go a bit deeper on that. The graphic here explains the flow. You know, I think you all will get it just staring at this. We're trying to do online inference and real-time process control. So everything that we'll talk about today is geared towards solving that problem. And we're trying to solve it in a fairly short time scale. So we're operating in regimes of hertz, more or less. We think we could probably go a lot faster, actually. So this is a very different situation than you would find, like, say, in an oil refinery, where you do have predictive types of controls that are operating, but the time scales are much slower. You have time to do things like run big solvers and do a little more math, if you will. So once again, a lot of the choices that we've had to make and what we've built and how we've designed it is really geared towards solving that problem. So we are turning over the settings for parameters of large scale industrial production lines in real time to ML algorithms and letting them drive the line in a closed loop fashion. That, our opinion is, that's pretty unique. We actually tried very hard to buy a solution like this. We worked with a couple of companies. We'll talk about some of that today. We actually had a couple of failures with some quote unquote AI companies that we brought in to try to build this with us before we felt like we could take it on and try to do it ourselves. We do think it's fairly unique. There's a lot of applications in machine learning and manufacturing environments. A lot of what we've seen tends to be sort of ex post. In other words, give us your data from the plants and we'll do some analysis, we'll do some categorization of factors and try to give you insights into ways to improve your quality. That's great stuff, and we love companies like that. That is a very different thing than what we're doing here. So to do it, we broke the data science into two stages. We have to get data, first of all, obviously. So we did do some work to develop what we call a transport layer to take data out of the machine layer, which is over at the far right. I think in this case, the plant is brewing espresso. We got to get the data up and out so we can use it. And we built some technology to do that. Then we have to go offline to model. And so we take it in two steps. We first have to model the physics. We build a physics engine of the process. This is an input-output model where we're able to take streaming data coming in and predict outcomes on the production line that we expect to happen in the next minutes, typically. We call that our physics package. That then goes into another environment where we are training the controller models. And specifically, the way we're doing this now is with reinforcement learning based controls. So it's it's a lot closer to teaching computers to play chess or Go, or the way that they're training self-driving vehicles. We're using similar types of algorithms and training self-driving controllers that can grab a hold of the process and keep everything running smoothly, as well as giving us a lot of really interesting insights about what's going on. That gets deployed as a controls package, and that's a very lightweight object that runs on the edge real time for inference, and that's what's actually driving the line. So a couple stages to make this work, but ultimately that's the system model, if you will. I will say one of the sort of artistic pieces of this, if you will, is the balance between sophistication and speed. So I mentioned that we're trying to drive processes on the time scale of a second. We don't have a lot of time to do fancy feature creation, to do really fancy digital signal processing, and even to execute very complicated inference models. The lighter weight that whole pathway is, the better shot we have of turning those controls decisions around in the speed that we want to go. And our experience is that it's always possible to build better models, but we're engineers, we're not theoretical data scientists. So the question is, what's good enough? And a lot of what we've built and the way we've balanced this pipeline out is really geared towards solving that problem. So another question you might ask is why we're building it. So what? And this slide really gets at the answer. Cooper Standard is in a segment of industry that falls in this chain here. So this is very different from, say, assembly of automobiles on a production line with discrete operations, we're talking about continuous flow manufacturing. In our case, we deal a lot with chemicals, with polymers, but also we know that what we're doing is applicable to some other extrusion-based industries, whether it's wire and cable, for example, some segments of food and beverage industry, anything with continuous flow processing that has reasonably complicated process physics is potentially areas where we can play. Specifically in our space to date, there is huge opportunity to improve waste, to reduce scrap. These tend to be very energy intensive processes. So, any time you can run better and less wastefully, you have a big environmental impact in terms of energy, in terms of waste products that aren't friendly to recycle. So a lot of high leverage from solving this problem and doing it better. This slide is an example of one of our pilots, just to give you a little more insight into physically what we're working on. The part that you see here is what we call a sealing profile. So this goes around doors and windows in vehicles. And although when you get in and out of your car, that may look a little simple in terms of what that thing is, it's surprisingly complicated, and it has to hold very tight tolerances to prevent water leaks in your car when you're driving on a highway and it's getting sprayed with water at speed. And these types of products are typically composed of 5 or 6 different materials. Most are polymeric. They are reactive, and so when you blend these material streams together to extrude these parts, you have a lot of physics going on. You have chemical curing. That's all influenced by ovens and temperatures. You have physical forces pulling this stuff down the line. You have gravity trying to make it sag. And worst of all, the raw materials for these kinds of products are polymeric, but ultimately organic, right? And no 2 barrels of oil are ever the same. And so no 2 batches of plastics or rubber that we would get from my suppliers at companies like Dow and Exxon, they're never the same. They're supposed to be the same theoretically, but they aren't. And those differences turn out to be really important because of the highly nonlinear physics in these processes. And ultimately, that's why they've been difficult to automate and control in the past. And just to make it worse, in case it didn't sound like a hard problem already, we have, at this point in Cooper Standard, about 20,000 SKUs that we make. Each one is different. It's different materials. The designs change frequently as the end users update their designs. The raw material selections change frequently as suppliers of these materials decide to discontinue things they don't want to make anymore. And the production lines change. Equipment changes, gets moved around, and what have you. So very difficult problem. Even if you can sort of tune a controller, let's call it the old school way, it's immediately irrelevant. And so we have to have a different way to attack this problem. Some of this I talked about. We do have to hold very tight control. We're talking tenths of millimeters on some very squishy and variable products. These tend to be high-speed extrusion operations, so stuff was just flying off these lines. A lot of nonlinear dynamics. You have, again, physical forces. You have chemistry. You have heat transfer. A lot of complicated flows mixing. So not an easy problem, actually. We went at this originally. I guess this was more than 2 years ago. We tried to do it the old school way. And I assembled a group of some very, very talented controls engineers. We went and took one product out of the 20,000 on one line and said, look, can we just beat this to death and try to get this in tune using, classical techniques, right? PID controls, cascaded PID control loops. And lo and behold, we were able to make some improvements. So the black line is an averaged value of a dimension on these cross sections that we're extruding. In this case, it says measurement 11. We might measure a dozen or more at any given time. And you get a sense for how much it varies during the day. And a lot of that has to do with batches of raw materials that are coming through, maybe the plant ambient conditions drifted, whatever. And the black line sort of smoothed out so you can see it. The pink line underneath that is the result we got after 3 months of trying to hand tune controllers. Let's call it, again, the old way. If we smooth that line, it would look a lot more like the black line. And believe it or not, it's about 50% of the variability is what that winds up being. So we said, look, this is theoretically solvable. We just need an approach that scales, and putting armies of controls engineers, watching every part and tuning stuff daily is not going to cut it. We couldn't hire enough thousands of controls engineers. So we began to try to use machine learning to design the controllers. That's when we got into the RL techniques. Lo and behold, it turned out to work really well. And you can see this is real data from one of our first attempts at this. I think it was January of 2020, in fact. And based on this success, we decided now we have a technology to design and deploy these control systems that we think we can scale globally. Now we think we have a company, and that's when we set up Liveline in February 2020. All right. So, compelling results. Nice pilot, but now we got to make it work at scale. I mentioned that there are a lot of knock-on benefits here. Obviously the reduction of scrap and waste and energy has a bottom line impact, but beyond that, once again, these types of industrial processes tend to be very energy intensive, tend to produce stuff that can't be recycled easily. We want to cut that as much as we can. I personally am super excited about the middle part of this page, almost as much as anything else. One thing you will find with these industrial processes is the plants tend to be old. They because they're so manually intensive, and because they have such tricky process physics, you will find very seasoned, very experienced operators and technicians in these plants. And we have facilities where we have products that there is literally one person in the facility that has the intuition and the touch to keep that line in control. If they don't come to work, we can't make those parts. And it's a very difficult talent question, because these aren't necessarily glamorous jobs where you're watching these industrial lines and essentially looking at dials and making little tweaks to knobs all day long. And it's not easy to go find great talent and say, hey, why don't you come here and stare at these dials for a year or two until you get a feel for this line, because it's really touchy and complicated. And then maybe you can, drive the line after that. And so we are very excited about transforming the way that people interact with these facilities and really upskilling these jobs. Now you're interacting with intelligent systems. Now you're getting predictive information, and hopefully can get ahead of stuff, start working on improvements, process improvements, instead of just reacting to try to keep, the wheels from falling off the process. I think that's cool. I think that's going to help us in terms of, having interesting jobs and being competitive, even staying onshore as well is really important. So, all right. So in summary, at least in terms of the company, and we'll talk more tech in a second, we're trying to automate the creation of the automation. So we're trying to learn controls from the data and then use those controls to operate equipment in real time. And then a lot of benefits we think are going to come from that. Okay. I will tell you, I don't have a slide in here on it, but in terms of our pilots, what did we see? So we were in 3 facilities, one in Michigan, one up in Canada, and then one in North Carolina. And we saw in those facilities scrap and waste reductions 58, 52, and 57% for those 3 pilots. So pretty compelling. This is not just a little better, this is a lot better. And we saw reductions in unplanned downtime in these facilities on the order of 80%. And that's just because as everything stays in control, there's less blockages and jam ups and things that happen in the lines. So very, very compelling pilots. Again, this is not marginally better, at least for these kinds of industrial processes, it's significantly better. Okay, so I'm going to talk a little more tech here. I guess I can pause if there are any questions. We can take them here. Otherwise, I'll keep going. Good.
So Chris, probably good to keep going. If people ask questions at the end generally.
All right, I'll keep going. So we did a lot of things the wrong way. We went down several blind alleys trying to solve this problem. And I don't usually talk about those, to anybody but technical audiences, because most people don't care, I think. But I thought maybe you'd find this interesting. So we did start originally down the journey looking at open loop simulation based control. So again, very complicated physics. The picture you see on the page is a fluid flow simulation, CFD, and it's looking inside of a die where we're combining the flows of two different polymers, very high pressures, high temperatures, and then they're getting extruded out. In real life, we're typically doing 4 or 5 of them together, along with things like metallic cores that we're inserting into that and pulling it through. Very, very complicated flows. Again, not to mention, the material rheology is changing with temperature and time. Right, these materials are curing and they're cross-linking and all sorts of interesting things. So not the easiest problem to simulate. Then there's all the downstream stuff going on with ovens and curing and other mechanical factors. So we did try to sort of make the grand simulation here, but it was a bridge too far, and there's just no way to do this in any reasonable time. Certainly not in the context of any sort of control loop, and so we did abandon that fairly quickly. I showed you a graph earlier where we tried to do it again the old way. This PID box here at the top left is in that flavor. It is theoretically possible to muscle this to death, but the analogy I would give you is, how about try to teach a computer to play chess and do it with PID control loops, right? Is that theoretically possible to do? I don't know, maybe it is, but I certainly wouldn't try to solve the problem that way. And that's more akin to our problem than a simple type of regulator on a single piece of equipment, right? Many pieces of equipment in complex physics. And there's some other approaches here, for the controls nuts in the rooms. You can look at these and agree or disagree with me on the pluses and minuses. But at the end of the day, we did gravitate towards a pure ML based approach that I'm gonna talk about. Okay. We did do one more thing though before landing on our answer. We did try to use MATLAB as the basis for some ML-based controls methods. A lot of us with controls backgrounds said, look, we're trying to make closed-loop systems. Obviously, we go to MATLAB, right? We go to Simulink and design it. Isn't that what you should always do? I guess the best summary I can give you is that MATLAB is not the advanced data science tool of choice. And there's other issues. Licenses are cost prohibitive. It's expensive stuff. Integration of ML models is not trivial in this sort of environment. And then our edge compute strategy is not clear either. There's better ways to do it than to try to force fit this into that tool. But we did try. So what are we doing? RO-based controllers. A lot of strengths with them. They are self-designing in a certain sense. So it does give us a dramatic reduction in the engineering workload and the data science workload, and ultimately is the key to helping us to scale this out globally. It really naturally accommodates some pretty sophisticated trade-offs that we have to deal with in terms of our objective function, or cost function, if you will. So I'll give you an example of that. If we were just trying to hold a numerical dimension to spec, that's not so bad. But we may have sort of Boolean style characteristics that we care about, right? Does it meet this characteristic, yes or no? A very nonlinear objective. And reinforcement learning models tend to be pretty naturally accommodate some very sophisticated, relatively complicated reward structures. So that's a big benefit to us. The other thing that's really cool is that the infrastructure it takes to do the reinforcement learning at scale it does enable some additional functionality for us. So what do I mean by that? As part of the core engine, the RL agents, excuse me, if you're familiar with the RL approach, are looking at information. And one of the pieces of information is predictions about how the line physics are going to evolve the next few minutes. And because we know that, we have the ability to raise, for example, triggers that, not only is the process going out of control, it's going out of control to the degree that we don't think we will be able to compensate for us in a few minutes. It may be okay right now, but it may be going in an uncontrollable state in the future. And so we can raise a flag and call a human operator over to come check on stuff before it gets too far out of hand. That is some, as you might imagine, some pretty useful functionality. And then the other thing that we like about this approach that we're using now is it opens the door for data scientists to work on controls problems. And trust me, if you go out and try to hire data science, but you require them to know how to use Simulink, you're not going to get a lot of applicants. So we're using now a technology stack and tools that are 2021 data science mainstream, and that really helps us to get talent in the door and for people to begin to engage and start being productive right away. There's some weaknesses to it. RL training tends to be computationally pretty intensive. It's much more intensive, in fact, than training the physics models that we use as part of the engine to train the RL. Those physics models can train in minutes on good hardware, and the RL, can easily take an hour or more. And because of that expense, it is not, you can't be naive about tuning these models, right? So if the computation was cheap, I might set up a grid search of parameters for the models and just go train a bunch of them and pick the one that I like the best. Very typical approach in data science, but that becomes computationally prohibitive for the RL. So we have to be very creative about how we're tuning the models. And that's an active area of research for us, actually. We have things that work. Again, we're engineers, right? So that's great. But time is money. And so we're always interested in improving that sort of stuff on the back end for us. And we have some pretty cool R&D actually happening on that right now. And then the last thing is that the RL controllers do tend to be pretty active. And so we have a couple of strategies to regularize those, both in training, but also after they're deployed. We do some different types of filtering and guard railing of the decisions they're making. And it's also an interesting area. I did mention the enhancements or the additional functionality that we get excited about. So, the core tech that we built is solving the blue bubble on the left, right? Real-time process control. But it's a high leverage problem because the infrastructure we have to put in place to do that, by definition, allows us to be very predictive about physics and drawing other inferences from that we can use in addition to doing the control problem. So, predictive alarms, predictive maintenance, predictive quality, semi-automated solutions, right? Advisor type things. That is all stuff that for very, very little cost, essentially front-end app development, we can expose that functionality, some of which actually already exists inside the core stack. So those are additional products for us, and we think is one reason why Liveline has a chance to be a successful company long term. So cool stuff. In terms of our tech stack, this may be too much information, but I mentioned that we're building it from hopefully a 2021 data science viewpoint. We are hardware agnostic. We're very containerized. We can run in the cloud. We can run on-prem. The one thing that's maybe a little unique here is because of our application for real-time process control, we have to do inference on-prem at the plants. And why would we do that? The reason is because we can't make the plants rely on any kind of connection to the outside world to be able to keep running, right? So inference is always local. But the harder, training offline, that's all tends to be to cloud. But once again, we're very containerized the way we built this, and we're agnostic. We can go sort of anywhere we need to go. The other thing that I think is unique about this application is this little line down in the plants that says the OPC UA bridge. So OPC UA, if you're not into industrial controls, is a very common communication protocol from the machine layer, the SCADA layer, if you will. And we plug into that, and then from there we take the data streams, and we are using Kafka, which is a large-scale pub/sub messaging protocol, I believe developed by LinkedIn originally. And we've leveraged that open source technology as a distributor, if you will, of the data. And it's essentially getting published to consumers that live all up and down the stack, whether it's the stuff up on the cloud, whether it's the on-prem stuff for inference. They're all listening to those Kafka message streams, and that's our backbone to do it. It's very high speeds, very lightweight, open source, cool stuff. And we got some folks here that did a very clever job of building that bridge. So lessons learned. So here's a couple, I guess, thought starters for you. So one is this mysterious Venn diagram at the left. So this is a Venn diagram, and you'll notice that it doesn't overlap a whole lot, right? Maybe a pixel or two, and that's intentional. And at the left, you have controls engineers, and at the right, you have data scientists. And I think one of the things that we learned the hard way was when we engaged with pure data science companies, and we tried to, by the way, we didn't make a lot of progress. And ultimately, it was because they didn't understand the application, right? We could try to tell them, but there are so many implications from our application that go all up and down the whole data science stack, if you will, to do it at least what we think is the right way, that everyone has to have a grasp of this thing from end to end. So we finally made progress, once our controls engineers began to get more fluent in data science. Now we have hired a couple of data scientists, but believe me, we put them through boot camps on controls when they came in the door. That, combination is where the magic really happens, right? So, maybe another way to say that is, being very clear on the end application and the problem you're solving, and having domain expertise on that problem is really the key to getting data science to work. So, maybe not shocking or maybe an obvious thing, but it was a lesson hard learned. The other lesson that we had to learn was dealing with this data science stack in a streaming context. And a lot of what you will do when you learn data science is work in batch problems, right? Where you have a data set, it's saved somewhere, it's sitting in a CSV file or in the cloud, and you work on a batch of data. We're working with high-speed streaming data. And so you have to be very careful about how you structured your digital signal processing, your feature creation, and make sure that it's compatible between offline batch training and online inference. And it may not sound like it's a big deal to you, but there are some caveats that we discovered to make that work effectively. And so it's been an interesting problem for us. And then the last one is just the digitization. And ultimately, nothing works without the data. So we have to have good data the way we want it. And we do have several very talented people on the team that are experienced in this stuff and speak SCADA and PLCs. And obviously, that's a key part of making this reality. So I'm just about at the end of the talking time. I'll leave you with a couple thoughts from the live line view about data science. I know this is the Mekki audience, but might be interesting for you. You'll see some things listed here. These are things that we find that we have to train data scientists on. And if you start at the top, you've got things to do with feature creation. So DSP techniques, digital signal processing, I don't think I've ever interviewed a data scientist that really had a feel for frequency domain analysis, which is, bread and butter for most of you probably, and why it might be useful to be, working our problem in blended domains, time and frequency. But it turns out to be really important and very useful for what we're doing. Basic control theory, right? Not everybody, dreams and PID loops if you're a data scientist. So we usually have some work to do there. I mentioned the end-to-end understanding of what we're doing, and why from a solution goal standpoint. And then finally, this is a really big one. And I would say, this is probably a good one for you, even if you don't want to be a data scientist. You will code at some point in your career if you're technical, right? That's just the way it is. And we do find that even with very good data scientists, we often have to train them up to be able to write production code. They can all write Jupyter notebooks, right? They can all do prototypes on their local machines or on a machine in the cloud somewhere. But it does take a very different mindset to write good production code. And so clear thinking about APIs and object-oriented programming practices, documentation, doing that well, and maybe most importantly, writing code for clarity rather than cleverness. And for those of you that code, I like a very clever regular expression as much as the next person, but I would never put a complicated one in code because the next programmer can't understand it without calling you. And so, being able to write code for the next person, not just for yourself. Believe it or not, we tend to have to train data scientists and that stuff. So again, this is about data scientists, not about professional programmers who live and breathe this stuff. We just find there is a skill gap. In terms of our tech and what else we're working on, we're always trying to further automate the whole stack and try to get it as hands off from the data scientists as we can. We're not quite there yet, but that is the goal. I talked about the efficiency of training and tuning RL models. It is computationally heavy. We're always trying to push that one. Just recently, we started to work on Bayesian techniques for reinforcement learning. We've done everything in a frequentist view, and we think there may be some benefits to moving to a Bayesian ML framework. So we'll see, but really cool area of work for us. We have some real practical stuff that we're working on this year, building an operations center to monitor the world. We haven't done it yet. We are going to be working on fancier front ends and nice apps, productizing the stack. So a lot of fun stuff coming. So I think I'm right on 41 minutes. There we go. So we're out of my time, and with that, I'll open it up.
Chris, thank you very much. So I send the virtual and the physical applause. We do have a bunch of questions, but let me just take host initiative and ask the first one.
Sure.
And sort of how you approach the as built versus a new facility. Like, so if you're going into an infrastructure that uses PLCs in a particular way, running these control loops, do you have to throw it all away and start from scratch, or how do you sort of inject into what currently exists?
Yeah, that's a great question. So one of our goals from the outset was to make the technology affordable for anyone. And if we only wanted to go sell, this technology to, GE or somebody, we might be a little more careless about that. But we had a goal to make this tech affordable for any size company, even small businesses, right? And Cooper Standard's not that big of a company, and most players in our space are even smaller. So from that view, you can't throw it all away, right? So we had to be very agnostic to what's there, and learn to work with it. The good news is that if an existing facility was built anytime since the 80s, they've probably got PLCs, and if they have a PLC and it has a data port on it, we can take it from there, and we can typically map those out. Whether it's whatever brand of PLC, we can map that their sort of tag schema into what we're doing, and that's just a one-time setup. And from there, we can pull the data and do our thing, and push down the new settings into the PLC once we've mapped their tags. And so we have not had to scrap a whole lot. We tend to work with what is there, but we're also just we're a pure software play, right? We're not trying to sell hardware or force people to use certain types. We're really trying to be agnostic to that. That's a great question.
Great, thank you, Chris.
Yep.
So let me go to the audience questions. There are a couple. Let me try to paraphrase. Asking around the lines of the specific types of reinforcement learning models and what machine learning techniques are you using?
Yeah, so first of all, just in terms of big picture, right? I mentioned we've been doing frequentist-based modeling. So, and that's, I guess, the normal types of RL or machine learning that you would do. And we're just now starting to work with Bayesian RL models, which is a whole other animal. But we're not far enough along in that I can give you a lot of insight. We suspect for some certain reasons that may be fruitful for us. But we work with models that you would read about, and if you've been through tutorials in RL, we tend to work with actual critic models a lot, Q-learning models. I'm assuming the person asked the question is know what I'm talking about here. So DDPG would be an example of an algorithm that's effective for our problem. So we haven't invented new RL algorithms. Actually, I think what's unique about what we do is the context that we present to the agents that we're training. So what do I mean by that? We're able to present agents with not just recent data from the past, but also we have this physics model, right, embedded that we've trained separately. We're able to also feed the agents predictions about the future in the presence of no controls changes, and then the agent can model what happens if it does try to make a change. All that actually can go into training these models. So if you think about what I just said, we sort of have a predicted feedback loop built into the system, and you can have a beer and argue about, are we crossing the line into like model predictive control? Yeah, we sort of are, but most definitely in an RL environment. So maybe that's too much for the question here, but
that was great. Let me pick another one off here. You're trying to solve real life production problems, but how are you dealing with the data overload? How do you shuffle between data features and what's an important feature, what's not, and what are the techniques? The question here in particular was asking about PCA or principal component analysis.
Yep.
How do you pick your features?
Yeah, it's a great question. We have several ways that we can do that in practice. One way is we can use PCA for sure, and that actually PCA becomes useful, especially when we create a bunch of synthetic features that we don't know what's going to be important. So I'll give you a specific example. We will often do wavelet analysis in the frequency domain. So think of it as a better version of FFT, right? And in the wavelet analysis, we will spawn, for every real signal, we might spawn a dozen new features that come out of the wavelet analysis. And a lot of those are not so useful. And so we will use PCA to take 200 new features and crunch them down to 5 or 10. So we do a lot of that. We do some other basic stuff. We'll look at quality of signals from an informational content. And so what I mean by that, well, if we have a signal, say some temperature sensor, right? And pretty much all the time, day in, day out, it never really changes, and it just sits there at whatever 200 degrees Celsius. It's not informationally useful, and so we have some automation where we pick those things out and just get rid of them because it's distracting, and try to boil it down to signals that contain dynamics about the system, right? Because that's what you have to be able to train, and so we I guess maybe the summary comment here is we're always trying to make sure we have the most informationally rich data set, not just data, and because the reality is the historical data sort of 95% of the time it's always the same, right? Production lines run, and most of the time they just run and it's okay. We care about the times when it's not okay, and so we do more picking stuff out temporarily than we do picking signals out in terms of the signal itself, right? If that makes sense.
Thank you for that, Chris. So let me sort of ask one more sort of synthesized question here. Sort of broadly asking, so this is in the context of Industry 4.0 smart manufacturing. So what are your thoughts on Industry 4.0 and what's going to actually take off versus not? And then intersecting that with what should we know, what should we focus on as manufacturing educators that are going to be useful for mechanical engineers wanting to go into this pathway of work?
Yeah, so Industry 4.0, I will tell you, in the C-suite and corporate America and Europe even, has gotten a bad rap. And has got a bad rap because 20 years ago, all the consultants came in from BCG and McKinsey, whatever, and said, hey, you have to pay us a lot of money and we'll make an I4O strategy for you. And a lot of that stuff never really yielded a lot of financial benefit for big companies. And the classical example I'll give you, and this is stuff that I've dealt with in my career, is a company decides they're going to spend millions of dollars, they're going to wire up all their equipment, and they're going to have an app where executives can sit and see which equipment is running and which is not running all over the world. And my response to that is, how does that make you money as a company? Because it honestly doesn't, right? And there's nothing that I can do as an executive sitting here, in Ann Arbor, Michigan, if I see a piece of equipment and Brazil is not running right now. So there was a lot of stuff like that in I4O that got done and never really made an impact. So it's gotten a bad rap. One of the things that we're trying to do is stay very, very focused on tech that helps, right? That actually makes a difference immediately in the plant. And so my best guidance on I4O is have a clear problem statement and focus on technologies that you think can efficiently solve that problem. And I guess that's good engineering advice in general, maybe, right? But certainly applies here. Just because you can put it on a digital dashboard doesn't mean that you should.
Very cool. Thank you, Chris. So excellent talk. Very exciting to see the work translating into practice, and very excited to hear about your continued successes. So again, thank you for sharing and for your time, and wish you all the best. So participants, thank you for joining us. So we will have our next speaker in 2 weeks, so April 14th. That'll be Dr. Richard Weissman, who's also an alum of the department, and has a very interesting career as the Vice President and Chief Technology Officer at Kinetic. And I believe he'll be sharing a little bit about Kinetic and also the new company that I believe he's getting involved with. But come back in 2 weeks to hear from Dr. Weissman. Until then, if you have recommendations on people that you would like to hear speak, including yourself, drop us a line. It's our opportunity to engage with faculty, with students, with our alums, with the community that surrounds us, and have content and information that's relevant and interesting to you. So again, thank you, everybody. Chris, again, thank you. Everybody have a good day and stay safe.
Thanks.